Hey team, welcome to today's members webinar. The topic today is all about braking systems data analysis. Specifically, we're really going to be focusing mostly on brake pressure sensors, but I'll also touch on some other ones as well. So for a start, let's talk about why we have brake pressure sensors in the first place. So really using brake pressure is really, I guess, the most convenient way of measuring the braking effort that the driver is putting into the car. So the way we're doing this is we're plumbing sensors into the hydraulics of the brake system. So that means somewhere after the master cylinder, but before the brake calipers. And the idea here is that we can get some sort of measure or relative measure of the amount of effort the driver's putting into the braking system, which is important both from, well, certainly from a driving analysis perspective, understanding where someone's braking on track, understanding how hard and how they're modulating that brake pressure as they move throughout the circuit, but also from a performance perspective, from the vehicle's perspective. So we can look at how effective the brakes are. We can look at things like brake pressure efficiency, which is dividing the coefficient of friction by the pressure that we're getting, things like that. There's lots of different uses we can use the brake pressure for. Obviously, brake bias is another one that we'll get into a bit later in the webinar as well, which is a really important part of any vehicle analysis. If we just jump over to the overhead camera here, I've got an example of a pressure sensor. Now this particular pressure sensor is not designed for to measure brake pressure, but it's in form, it's really similar to exactly what you'd see for a brake pressure sensor. And what I mean by that is its layout is the same as far as it's got this particular one has a tapered pipe thread on the end. It's got an inlet on the end to interface with the fluid. And then we've got a 3-pin plug on the back. So you're going to have a positive voltage and negative sensor ground, and also the one of those pins will be for the sensor output as well. So normally, most often these like a 0 to 5 volt style sensor. This particular one is for much lower pressures. I think it's 0 to 15 psi, which is a 1 bar sensor. And even though that's measured, that's not intended for doing brake pressure. That's really the style of sensor that you'd expect to see in the system. So the other thing I want to talk about with these is how they're plumbed in. So I just want to go a little bit of the architecture, how they work. So let's say you've got your brake pedal up here. Your brake pedal's got it's pushing on some master cylinder here, and then maybe you got your fill on the top of the master cylinder there, and this has got a little piston that's pushing in here, and then we've got our brake calipers. So let's have a brake disc, and let's say we've got our brake caliper sitting down here, and we're going to have a hose running from one to the other. So the pressure in this hose is the thing that we're interested in tapping into. So there are a couple of different ways we can arrange these sensors in here. One of the common ways is to simply put a T in here. So we could T this, put a little T piece in here, and then we can connect our sensor here, and then we can run that wire off to our data logger. Alternatively, increasingly there are actually options with master cylinders that have ports dedicated for a pressure sensor. So that's where we would put mount the sensor somewhere in the master cylinder where it's got access to the same hydraulic pressure that is in the rest of the system. The thing I quite like about this system of when they're integrated into master cylinders like that is that it's a nice tidy way. You're not adding any extra components into the system. It tends to keep the sensors out of harm's way, not in a place where they're likely to get any damage or anything. So that is quite a nice way to do it if you don't have sensors already. And that's actually a good point to mention that a lot of road cars, or a lot of OEM style cars, particularly when they've got things like ABS and stability control, this information, this brake pressure information is already being measured on the car. And so the ability to be able to tap into something like the factory CAN bus and get that information out of the car, it means you don't have to run any extra hardware. So if you've already got this like this pressure sensing equipment in your car and you can access it from the CAN bus, which is quite common in modern cars, then the great thing about that is you don't need to do any of this extra hardware work or buying any sensors or plumbing and tapping into your brake system, anything like that. Obviously, if you're doing this, you need to be really careful that you're not introducing any problems where you can have mechanical failures or hydraulic leaks, because obviously that's pretty serious consequences there. The other thing I wanted to mention before we get into talking about bias later on, I wanted to talk about the layout of lots of factory brake systems. So the way the way certainly a motorsport style brake system tends to be laid out is with let's say this is our front axle and our rear axle. So it's the front of the car. So we've got our master cylinders here, or single, whether they're single or double. It's not really important for this point, but the idea here is that in road cars where you've got a single master cylinder, you're going to have some cars will be plumbed diagonally. What I mean by that is there will be one circuit will be the front left and the rear right, and another circuit will be the right front and the rear left. Now obviously they've got different pressure ratios, they've got different pressure sources out of the master cylinder, but the reason some manufacturers are doing this is because they want to, in the event, let's say you have a hydraulic leak, a brake line failure or something like that, say one of these hoses is gone, if the brake pressure system was plumbed with the front and rear separately, if now one of those fronts went, that you've got no front braking. And because it will not, you essentially got no front braking, but if you split them in diagonally like this, then at least if you have a failure in one of those diagonal circuits, you've still got one front brake left to do the braking for you. Obviously, the braking on the front axle is the one that's by far the most dominant as far as making the car stop the quickest. So that's the idea behind why they're plumbing like that. In a motorsport context, we don't do it like that. We generally, I'll draw a separate one over here. We generally have a separate front and a separate rear system like this. And the idea here, sorry, coming from two individual master cylinders, the idea here is that if you've got a you want to be able to vary the pressure ratio between the front and the rear axle. So normally when you're modifying brake bias, you want to change the amount of braking force distribution you've got in the front axle with respect to the rear. If you had diagonally plumbed systems, then you wouldn't be able to do that. You'd only be able to change the diagonal split, not the front to the rear split. So this is why in a motorsport context, we almost always have the axles split front to rear like that. And that's certainly by far the most common thing you'll come across. So if you are looking at making changes to your brake system or looking at plumbing brake pressure sensors in, that's just something to be aware of, is taking note of how your particular car is plumbed and what that means for your situation. So I just thought, now that we've talked a little bit about the actual physical layout of them, let's jump across to my laptop screen and we'll have a little bit of a look at some data to start off with and just see exactly what it looks like, particularly for people that haven't actually seen it before. So here at the top of the screen, I've got a speed trace for a given circuit, and I've got two other channels plotted here. Now I've got the front brake pressure shown at the top and the rear brake pressure shown at the bottom. So I'm just going to zoom into one particular braking zone here and we'll have a little bit more of a look in detail. So obviously what's happening here, we've got no action or very little action on the brake pressure as we move through this section. You can see on the speed trace, the car's still accelerating at this point on track. And then we see a relatively steep climb in the initial brake pressure, and that's happening both on the front and rear axle. So in this particular situation, it's a motorsport style pedal box, so you've got a front and a rear master cylinder side by side being operated by the same brake pedal. So it's two completely separate hydraulic systems, one for the front and one for the rear. So as the driver moves through the stop, so he makes more or less his biggest brake pressure will happen at the start of the stop, and then he's sort of gently bleeding off the brake pressure here. We'll talk about some of these features a little bit later on in a bit more detail, but he is bleeding off the pressure before bleeding completely off, and as he gets to mid-corner here when the speed is the minimum, he's got no pressure on either of those hydraulic cylinders. So let's just break down exactly what's going on here as far as these phases. So we've got the initial hit, which is this point here, which is the first point we see the pressure starting ramping up. Then this next section here is when we get to this point here is really just getting to the peak pressure. So our peak brake pressure is at this point here. So one of the things we're often interested in is the time. So to go from here, I'm going to put a reference there and put a second cursor there, and we can read off down the bottom here. So that's 0.38, or let's say 0.4 seconds it's taking to get that driver from initially hitting the brake pedal to modulate to peak pressure. And that's really one of the critical things in braking, is getting to that peak pressure, but not only getting to it quickly, but getting to it accurately to not overshoot or undershoot your target pressure. And that is definitely one of the skills that comes in with being a professional driver. Now there are these features throughout here, these little dips in here, and what I think that they will be throttle blips. So let's have a look. Let's add in some throttle trace in here as well. Yeah, so what we've got going on down there is see these little blips in the throttle as they go. This is going down 3 gears in this case. So you can see these dips in the brake pressure each time we've got, we'll see differences in the brake pressure modulation each time the driver is blipping the throttle. So this is where the heel toeing the throttle on the way down. This is a really difficult skill, and this is definitely not the worst amount of brake pressure modulation, but the ideal situation is you do want it to be completely smooth. What I mean by that is if we were to take on the front here, we would ideally want that bleed to look something more like this. That's sort of our ideal default bleed profile that we want to see. Now, it's really not trivial to get it working properly, to get that heel toe going properly, but in this case, this probably is a little bit too much variation that we're seeing here on the brake pressure. So the other thing I want to talk about with brake markers, because this is something that we are using for analyzing where people are doing their braking. So one of the most common metrics you'll be using when you're comparing, say, two setups to each other or two different drivers to each other is looking at their braking markers, looking at where they're braking on track. So what I'm going to do in this example, I've just flipped over to a different view here. I should probably explain this first. This is just gives us a little bit more information about how of the different driver inputs. So we've got engine speed at the top. We've got the vehicle speed here. I've got the throttle and brake sitting over top of each other. In this case, I do actually have them overlaid. I do that intentionally. I do that to save a little bit of screen real estate on my screen. It allows me just to compress things up a little bit more by having both of those channels on the same line. And because you're generally only using the brake or the accelerator one at the same time, not at the same time, they don't tend to overlap or cause too many problems with each other. So often I have them overlaid like that. Then we've got the brake bias shown here, which I'll come back to, and we'll get in a bit more detail about that in a minute. Steering angle and the gear position. So as I said, the way one of the ways you're often using brake pressure data is to understand when on track, but also with how much intensity the driver is actually braking with. So let's add an overlay in here. I'm just going to use a different lap here as an example, even though this is from the same driver. But for argument's sake, let's look at a place on track where we have a difference in the braking marker. And I can see down here, looks like there's a difference. So here at this point on track, we can see that we're accelerating down the straight. Then we can see in the green channel here, this is the accelerated channel, that the driver is lifting off the accelerator, and we see the two different brake pressure traces here. So what I can do is, again, use my cursor trick, so I can put the cursor at the point where the brake pressure starts ramping up in Motec, which is what I'm using here, but the process is really similar regardless of the data analysis package you're using. All data analysis packages have the same functionality of checking for deltas or differences like this. I'm going to put the second cursor on the point where the other brake marker is starting, and then I come down here and look at the difference. We've got 9 meters, so let's say a 10-meter difference between those two braking markers, which certainly it's absolutely like a pretty that's a pretty big difference. You'd expect a professional driver to be able to brake really within sort of 1 to 2 meters, maybe 1 to 3 meters, depending on the part of the circuit of repeatability. So there's probably something quite different going on in the car here. It may well be that they're braking earlier in a later run because they've got a tyre issue or a tyre degradation issue. Maybe they're braking for some traffic, whatever it is. But this is just really important information to understand when you're going through and doing a bit of driver training to look at where someone is actually braking on track. Obviously, it's important, like we've discussed in the past, that you do need to be making sure you're looking over a distance scale rather than a time scale on the bottom. We want to make sure we're comparing the same distance, the same position on track, not the same time into the lap, which we've gone into a lot more detail in the past. The other really important thing, like we talked about, is looking at the brake pressure itself, the actual magnitude. So let's zoom into another part here. We've got a couple of different examples of the peak brake pressure. So here in this colored example here, the driver is using much more peak brake pressure initially compared to the peak that they're getting in this first place. So let's just put a delta between them. You can see here that we've got, sorry, let me just get rid of that. Let me just make it a bit clearer if I put it here. So we've got 112 bar at this point, and at this peak, which is much later in the stop, it is versus 86. So that's a pretty big difference in the brake pressure. So again, you can just see this is a really useful tool for understanding not just where we're braking, but how hard we're braking, with how much intensity we're braking. So this is probably one of the, certainly when you're training, well, any driver really, but particularly when you're training, when you're an engineer working with amateur drivers, looking at that brake pressure trace is probably one of the things you're going to be spending the most time on. Braking tends to be the thing that people find the most difficult. It is the most difficult thing to get right in the car, as far as being repeatable and your brake trace being right, your style of braking, all of that stuff. As well as your bravery, as well as how deep you can go into the corner as needed. All of these factors mean that looking at brake data is probably one of the most common things you'll be doing, particularly when you're working with a less experienced driver. So let's have a look at next brake bias, like I talked about before. So what is the definition of brake bias? It's simply the definition is simply the front pressure divided by the total pressure. What I mean by that, we're doing a ratio calculation of how much pressure is on the front axle relative to the rest of the brake system. So I'll just sketch out the equation for that. Super simple. So our bias is equal to the pressure on the front axle divided by the pressure on the rear axle plus the pressure on the front axle. So that's simply going to give us a ratio, and then we can modify that by multiplying it by 100 to give us a percentage. So that's all I'm doing over on my laptop screen here in this brake bias channel. I'm just going to get rid of the overlay just to make things a little clearer here. Let's put our original data on. What I'm looking at is computing the proportion of hydraulic pressure we have on the front axle relative to the rear throughout the stop. So in this particular case, if on this arbitrary point in the circuit, we've got 52% of the hydraulic pressure is shared on the front axle relative to the rear. Obviously, every braking setup is going to be different. That number is almost, I wouldn't say arbitrary, but it's only really relevant for the particular braking setup of your car. What I mean is things like disc sizes, certainly the size of your calipers, so the piston sizes of your calipers and the piston bore sizes of your master cylinders. These are all going to be, depending on what relative components you got fitted to your car, this number is going to be different. It's not necessarily going to be tied to the weight distribution or anything like that in your car. It's just a reference number that we track over time. It's not something you get too carried away on, but it just gives us a relative understanding of where the brake bias is adjusted to. Now, brake bias is one of those things that is probably a little underrated as far as tuning the handling of your car. So obviously, as you enter a corner, the front of the car, you're transferring load from the rear of the car to the front of the car. That means we need a higher proportion of braking effort on the front axle to the rear axle. But depending on the position of track that you're at, so let's say you're at a high-speed corner versus a low-speed corner, you might want a different brake bias if you're changing it throughout a lap. Alternatively, if you're looking at something like a wet setup versus a dry setup, you generally have a different hydraulic brake bias from the front to rear for your dry setup versus your wet setup. What I mean by that is in the wet setup versus the dry setup, obviously we've got less grip overall. So that means we're not braking as hard. That means we don't have as much load transfer from the rear axle to the front. So almost counterintuitively, we actually end up winding the brake bias towards the rear when we have a wet setup. So typically when people think about putting the brake bias, it's relatively intuitive. When people think about putting the brake bias from to the front, if you're having entry oversteer balance, or you're having problems with keeping the rear end in traction on the rear end and braking, you might move the brake bias towards the front or from the rear towards the front. Alternatively, if you are having a lot of understeer problem, or particularly in the trail braking phase, one of the things you can do to help rotation is to move some of your brake bias to the rear axle. Another way to use it would be if you've got tires burning off, or you've got tire wear going on throughout a stint. If it's wearing more at the rear than it is at the front, you may have less braking capability at the rear, so now you may need to move the brake bias to the front. Alternatively, you may have fuel burning off if you're doing a long race as well, and that fuel burning off, depending on where the fuel is distributed within your car, is going to depend. It's going to change the static weight distribution you've got in your car, so you're going to need to change your brake bias to suit as well. So all of these different reasons I'm going here, these are just reasons to say that you've got often in high-end motorsport cars, well, not high-end, but anything with adjustable brake bias, you're typically adjusting your brake bias as you go, certainly between tracks, and in some cases as you drive around the track. You'll see in some series, V8 supercars is a great example, where you'll often see drivers making brake bias changes on the fly. So what you'll see maybe in another example, something like a prototype or a GT, typically the brake bias adjuster is just a knob which you just twist one way or the other, and generally the way that's being used is making a small change to the brake bias as you go. That's more something that you're making a change gradually, maybe a very small amount of a percentage as you click each click. This might be happening throughout a whole race stint, as the tires will change or as the fuel burns off, like I was talking before. In something like a touring car series, what you quite often happen is a different style of brake bias adjuster, which is a quick style adjuster. So you still have the ability to make tweaks throughout your stint, but you might have a quick adjust. That means you've got a lever where you can push it forward or back really quickly in a similar way that you've got a gear shifter. It might be a small lever sitting somewhere. The idea there is that they can make those brake bias adjustments quickly on the fly from one corner to another. So they'll have a predefined idea of which corners they want to shift the brake bias forward and which ones they want to move it back. Obviously, that makes it pretty busy inside the cockpit. It's not something I'd recommend for a first timer. It's more of an advanced thing that you get into. But this is some of the stuff that we use brake bias analysis for. Maybe I should just talk a little bit about how the brake bias is actually adjusted and why we're measuring a pressure difference as well. So I'll just sketch out exactly what's going on there. So if we're looking from the top view here, so let's say we've got our master cylinders, and if we took from the top view of the pedal box, I should say, so let's say this is at the top of our brake pedal, so this would be the driver's foot would be sitting on here pressing the brake pressure, pressing the brake pedal in towards the master cylinder. So you've got these little levers sticking out with a bias bar set up in here. So the idea here is that the brake pedal is pushing on this this trunnion, this bias bar, and both of this whole bar is distributing the force to both front master cylinders. And basically the position of that trunnion with respect to the master cylinders is going to depend how much of that mechanical force, what proportion of that mechanical force is going to be transmitted to the front master cylinder versus the rear master cylinder. So let's say that's the front and that's the rear master cylinder. Just zooming in on that a little bit, what I'm saying is if that's your bias bar and this is the connection to the master cylinders here, if we're going to move this, this trunnion is essentially on normally it's on a type of thread, and there's usually a mechanism to connect to the bias bar here, which is what that knob's connected to, which is essentially rolling that trunnion bar. The idea here is that as this connection between the brake pedal and the trunnion bar moves along, so as it moves left to right, if you move it more towards the front, you're going to have more of that mechanical force being proportioned to the front hydraulic system, and if you move it to the left, you're going to have more on the rear hydraulic system. So that's just a little bit about how that bias bar adjustment's actually working in there as well. I'll show you how we're calculating that. So if I can just come in here to brake bias, and we'll go to edit the maths for that. So just ignore the first part of this math channel for the start, but you can see the second part where it's implemented exactly the equation I wrote on the overhead before, which is we've got the front axle here, so this is front brake pressure divided by the front plus the rear added together. There is actually one other part I want to dig into with that. I've got this condition here, so in Motec syntax, the way they deal with what I want to do is get rid of the sections in between the braking zones. So let me just go back one step before I explain that. So you'll see here I've got the bias only be computed in the areas where we are braking. So anytime there's hydraulic brake pressure here is where we are computing the bias, and everywhere else I've got a blank value. Now you could show it 0, but when you're not braking, I myself find that a little bit cluttered. I like to make the plots as clean and as easy as possible to read. So I'll show you how I've got that implemented in here. It's using a choose statement. All this is saying is we've got 3 parts to this statement. The syntax is choose. All it means is basically a conditional. So it's saying when we are braking, so is braking condition equals 1. It's a Boolean operator. It's just saying when 1, that means it's equal to, that means it's happening. So when we're braking, do this calculation, and we've got a comma here, otherwise invalid. Invalid just means nothing, give me nothing. So show no value, don't do that computation for me. This is braking condition is simply a condition that I've put in there to define whether the car is braking or not. The idea here is that I can write a condition for that I can use in one place, and I can use that is braking condition throughout my analysis project. And I don't need to keep, for example, I could implement the same thing here by just saying when brake pressure is greater than 5 bar, for argument's sake, do this calculation. The problem is in lots of different math channels, I'm going to be wanting to use that is braking condition, and it means that you can end up with inconsistent ways it's calculated throughout your project. If you go and update it, you have to go through manually and update it in all of your different math channels. That's why I tend to define a single is braking condition that I can modify in a separate place, and I can update it. I'll actually show you guys what that looks like. So is braking. Let's have a look at the example for this. So in this case, it's using another choose statement. All this reads is it says that when the front brake pressure is greater than 50 or 50 psi, give me a 1, otherwise give me a 0. So then you can see, obviously when we're braking, we're going to get a 1. So we now go back into our original statement. So and that's doing a test to say is braking condition. If it's equal to 1, then do the calculation. So that's how that's working for us. That's my preference. You don't have to use a conditional on it like that. I just find it makes it a lot cleaner of a way to use. Obviously, as I talked about before, the way I'm using this channel is to understand how the driver is changing the bias throughout a lap, but also throughout a stint as well. So I'm only looking at a relatively short run here, but if you're looking at throughout a race stint, you would see this value evolve as well. Now, what we can see is if we zoom into one of these particular sections here, we can see there's a lot more variation in the bias as we get towards the lower pressures. And we'll look at another type of plot later, which is another way to visualize this. But essentially what's going on here, at the heavier ends of the brake pressure spectrum, the bias does tend to be more constant. At the lighter ends, you can see where the brake pressure is dropping off here. That's where you get more of that, more stiction, more any sort of hold-ups you've got in the whole brake bias setup. So there's a lot of different joints in the pedal box. What I mean by that is there's a whole lot of different bushings and bearings. And as you get lighter and lighter pressure, it means the friction in each one of those different systems tends to hold up one side of the master cylinder more than the other. So whether it can be any of the connections, any of those bearings or bushes causing that problem, it also can be different amounts of stiction you get within the bores of the master cylinders themselves even. It'll just depend on your exact system where those bias variations are coming in. Now, it's natural to get more bias variation on low pressure, so which is you're going to see predominantly more at brake pressure release than you see during the main braking event, but it's also important to realize that in some cases people actually use this to their advantage as far as having different mechanisms in their pedal box to actually bias their brake pressure towards the rear axle on brake pressure release. So the idea here is that on brake pressure application, the bias is exactly what you set it based on your adjuster, but it's the whole system is predetermined to set up that when you start only on the release direction of the pedal, that essentially you end up adding a little bit of extra pressure to the rear axle relative to the front that you didn't have before. The idea here is that it helps, adds a little bit of dynamic rear brake bias just on when you're releasing the brakes. Obviously when you're releasing the brakes, this is the time when you start to rotate the car into the corner. So for some cars that can be a big advantage, or some advantage when you add some rear bias to the car on corner entry if you're struggling with understeer in the first place. So this is again the place I would come to look at how much that system is working. Typically those systems are quite adjustable, so you can adjust it anywhere from having no effect through to having quite heavy effect, whether it's a linear or a non-linear effect depending on the system that you're using. This is one of the places you could come and visualize that by looking at the brake bias channel as well. The other thing I want to talk about here is the fact that I'm looking at, this page here is sort of my typical driver analysis page. This is this sort of information I'd be using when I was looking at the way the driver was driving the car. So I've got the steering, the brake, the accelerator, and obviously the gears as well. You'll see here this channel that I'm actually plotting for the brake pressure is brake pressure total. So I'll just show you what the definition of that is. That is just a summation of the front and the rear brake pressure. The reason I do that is because what you'll quite often find is have different drivers running a different brake bias from one to the other. So what I mean, the way you'll see that is, again, I'm just looking at one single driver here, so it won't show up too well. But when I've got an overlay here, you'll have an offset. You would have an offset of two drivers who are doing two quite different brake biases. This white line would be at a different point with respect to the yellow line. The advantage in looking at the brake pressure total is it makes the braking signal less sensitive to the bias. So let's say, for example, what I mean by that, let's say we've got two drivers with quite a different bias. Let's say you've got a pro-am situation where the pro is much more comfortable with a more rearward bias and the amateur is more comfortable with a more front bias because they find it gives them more stability on corner entry. Now, if I was to just plot the front brake pressure for both of those when I was doing the driver analysis, that could skew me because we've got a different brake bias setting. It might lead me down the garden path as far as making me think that one driver was pressing harder on the pedal than the other. So that's why I always use the total brake pressure. It just gives me a little bit more of an equal way. It basically takes the bias mostly out of the equation as far as how much brake pressure effort is being used. So guys, that's it for the most part of the demonstration. I have got a couple more things to go through in a second here, but if you've got any questions about any of this, whether it's about data analysis, braking systems, anything else that comes to your mind, any of our future courses, anything, you're welcome to chuck those in the chat and I'll get onto those soon. The last couple of plots I wanted to go through was adding in a couple more sensor types. So everything we've talked about so far has been with brake pressure sensors. So how much actual hydraulic pressure we've got in each one of the lines, each one of the hydraulic lines. There's also another type of sensor that you can use, which is quite commonly used in pedal boxes, which is brake position. So that's measuring, or more specifically, the position of each master cylinder. So how far each master cylinder is moving. And with that position and along with the pressure data, we can start to do some quite useful and interesting stuff as far as diagnosing problems with our braking system. So what I mean by that is if we come across to the overhead again, back to our setup where we've got these two different master cylinders, what I mean by that is essentially the way it works is usually just having a little linear potentiometer on each side, on each master cylinder. And the idea here is that not only are we measuring the hydraulic pressure in the hoses, we're also measuring how far each one of these master cylinders is actually moving. So I've got some data here to show you from the same car that we've been looking at. So here I've got, again, this is just a speed channel at the top. I've got our brake master cylinder travel for both the front and the rear, and then our same brake pressure channels that we were looking at before. That just here I've got them overlaid on top of each other, but it's exactly the same data that we were looking at before. So what's interesting to look at as we look at this straight away is that even though the pressure ratio, which is what we see at the bottom here, when we overlay the front and rear pressures, they're actually relatively similar to each other. You know, and as we saw in the brake bias number, that was roughly 52% at the stop that we looked at before, so that kind of makes sense. But interestingly, if we look at the brake master cylinder travel, the front travel has got a lot more than the rear travel. So we've got, let's say here, 11 millimeters on the front and 6 on the rear. So almost double the amount of travel. So that means that the bias bar is going to be skewing quite a lot as the brake pedal goes in. And that is actually an important point that we'll be getting to in a future course on braking system design, is on the setup of that bias bar. What you typically want is the bias bar to be flat when you've got peak brake pressure on. So that means you end up having to put some sort of offset into the bias bar to allow for the different amounts of travel you're going to get on the front and rear axle. So straight away, that's a pretty interesting thing. The other interesting thing that we see here, and we tend to see it more clearly, or in some situations you see it more clearly on the position channel rather than the pressure channel, is vibrations in your braking system. So in this particular car, this is a situation where there was some vibration on the rear axle. And you can see that's what these little spikes are here, these little relatively high frequency spikes as we move down the position channel. Now you definitely can see some of this behavior in the pressure signal, but because the pressure signal it just doesn't tend to show up as cleanly as it is on the position. And what that's going to mean is that that's something that the driver will actually feel coming back through their foot, because you're seeing there on the position. Anything you see on that position channel should correlate pretty well with the feedback the driver's getting through the pedal, because they'll actually feel, in this case where we had a rear brake vibration, the actual pedal will actually start vibrating a little bit. And so this is, if you do have a brake vibration, which can happen when you end up with warped pads, or sometimes if you get pickup on the discs, warped discs, or you can get pickup on the discs from during a pit stop or something like that, from brake material fusing itself onto it. This is the sort of thing you have, and in this particular case we can see really clearly that's a rear brake problem and not a front brake problem. So that's one interesting use for using the brake treble. The other is to look at it in terms of stiffness. So here I've got a couple of different plots. I've got a speed plot at the top here. We can see we're just looking at this single braking area here. Let's just zoom over this single zone, and you can see here I've got two XY plots and they're zoom linked, so they're only looking at the positions on track that I'm zoomed to. So let's just zoom in back there again. So what I'm plotting here in these XY plots is I've got brake master cylinder travel on the vertical axis and pressure on the horizontal axis. So this is a similar way to what we were looking at before, but looking at an XY plot rather than a time distance plot. It's the same information. The idea here is that the angle of this line is indicating something about our compliance or our stiffness in the system. So that's telling us how much travel we're having to use on the pedal, or how much travel we're having to use on the master cylinders for how much pressure output we get. So this can be a really useful way of overlaying two different sets of data to understand if you've got a brake compliance issue. So this is where something like if you've got a mechanical compliance issue would show up, or if you've got brakes that need to be bled because you've ended up with air inside the system. If you were to overlay one run where you know the brakes were good versus the one you've got now, if you were to see a difference in the trend or the angle of that line, that's going to tell you something different about the stiffness. So again, that's just a nice diagnosing feature. This is something that I usually, when I have a car that is running brake travel sensors. This is usually one of the sensors I have up on my telemetry that I'm looking at live, just to understand if there's anything changing with the brakes over time, because it can be a really nice test. The last piece of data I want to look at here, I'm just going to zoom out over a whole lap, is we're plotting here brake bias versus the total brake pressure. So you can sort of see this trend here. If I try and draw this cleanly as I can with the mouse, I've got one there and sort of another one like this, sort of this funnel shape here. And the idea here is, again, it's just giving us a way of looking at how much our brake bias is changing as we change the pressure, as a function of the pressure only. So obviously it's important that we're not adjusting the brake bias when we're looking at this, but what we want to know is we can use this to understand how much compliance and sort of how well our brake system is working. As I said before, like if you're not adjusting your brake bias throughout a lap, you want your brake bias to be as consistent as possible. Inconsistent brake bias, a different proportion between the front and the rear axle, is going to give you potentially quite nasty handling traits. It'll make things, make you start hunting down things in the car setup, whether it's suspension or tire pressures, stuff like this, when it can just be a brake bias problem that's hurting you the whole time and you didn't even realize. So what I mean by this is, again, this can be a useful plot to overlay from one brake system to another, but essentially we see something really similar than what we saw in the log data, which is at low brake pressures, we get a much bigger bias variation, and at high pressures, we get a much lower bias variation. So ideally, we want this spread of data in the middle there to be sort of as narrow as possible. We want that funnel to be as narrow as possible, particularly in the high end. As I said before, compliance in the system will tend to mean you end up with some, not some compliance, different stiffnesses in the joints and the suspension will mean you end up with a different spread of data at this end of the plot. But up here, you really want this to be as tight as possible together. That's going to be different for every car, every situation. But again, it's just another nice overlay to understand if you've got different compliance issues or changing brake bias with brake pressure, because generally it's not something you want unless you've designed it in there intentionally. Okay guys, that's it for the lesson today. I just want to remind you guys about new courses that are coming out. If you, everything we've gone through today has got particular relevance to our brand new course, which is our professional motorsport data analysis course. If you're interested in that, absolutely go and check it out. And if you remember, if you're not watching this live, we're not watching this webinar live, you can go back and check in our forum, our archive. All of our old webinars go into our archive, and if you've got any questions that come up out of this, you're welcome to ask them in the forum and I'll get to them there. But for now, let's jump across to the questions and I'll see if anyone has had any questions as we've moved throughout the webinar. Okay, question from Shane Plow. Optimum G released a technical article with methods for calculating a value to compare how aggressive you apply and how smooth you release the brake. Have you used anything similar and did you find it useful? Actually, funnily enough, I have used something similar. I actually used to work for that company back in the day, so I know exactly what you're talking about. Essentially, what you're doing is using, okay, let's start with your brake aggression. So let me sketch that out for you with what I mean by that. So let's say this is our brake trace here. We've got ramping up and then fading off into nothing here. So with brake aggression, what we want to look at is the slope of this line, and that's how quickly we're ramping up that pressure. So essentially what we want to do is a rise of a run calculation of that to look at the gradient, or M, as you might remember it from maths. We're doing rise of a run. So what we want to do, there's a couple of different ways you can implement that. The main way we want to do it is we want to take the derivative of it, but we want to first use a derivative to check that the brake is being applied, not released. So what I mean by that is when we want to do the brake aggression, we only, for the application aggression anyway, we only want to look at this section here where the brake pressure is actually increasing. And the way we do that is by looking at the derivative, so looking at the slope of it, which is something that's a tool that's built into pretty much every data analysis package. It's something I've gone through in previous examples. It's something we go through in quite a lot of detail in the professional motorsport data analysis course. But essentially, what the software is actually doing is, if I was to bring this down to the actual points that this is looking at, essentially between each one of these points, it's taking the slope between each one of them. Now, what's different you'll see is when we're applying the brakes as opposed to when we're releasing the brakes, is that each one of these little slopes is positive. It's going in this direction when we're applying, and it's going negative. It's going in this direction when we're releasing the brake. So if we're looking at brake aggression, we only want to calculate it when we're applying it. So for a start, we say only calculate when the derivative is positive. That's great. The next thing we want to do is we want to take the derivative or the average slope of this line as well. We don't have to take the average. There's all sorts of different ways you can calculate it. But one of the first things I do normally is that you'll see the brake pressure data is usually it's usually got some messiness to it. The problem with that messiness is it does tend to stuff up the derivative calculation, because when it's doing these little slope calculations up here, if you've got very messy data like this, these slope calculations can be going, they're going crazy like that. So what you first usually want to do that signal is smooth it. So if you've got a signal like that, you find a smoothing function that finds a line that sort of traces the trend of what's going on, but misses all of that high frequency detail. That's really what we want to ignore for the derivative calculation. Then after that, you can do the derivative on the smooth. So first we're taking the derivative to say only calculate the aggression when we're increasing the brake. Then we do smoothing the channel, and then we're taking the derivative of that channel. After that, you can do things like looking at either the maximum or the average of that channel over across a lap. Then you can plot that across a whole lot of different laps and look for a trend in the aggression, whether it's a difference in the trend between aggression between one driver and another, or a difference between as the run changes. There's all sorts of different ways you can check that. You also asked a question about smoothness, and it's got some similar stuff in there. So brake pressure smoothness, what that means is if we look at the same similar plot to before. But let's say our real brake signal looks like this. We want to quantify basically how unsteady that signal is, particularly on release, but it doesn't matter. It's for application, it's the same concept. So what we want to do here is the method for coming up with a number of how basically spiky or how unsteady the signal is. What we want to do is, again, you probably guessed it, we're going to use a smooth function, and we're going to calculate the smoothed version of this with sort of a moving average filter. And you want to do something that, again, you're finding that visually you sort of got to experiment with a different time period over which you're using that moving average filter. But you want to find a moving average filter which, again, calculates sort of the guts of that shape as closely as you can to that shape while you're getting rid of that high frequency noise. Then after that, we're writing a math channel at each time step that we're calculating this for, we want to find the difference between each one of these channels. So obviously you've got each one of these is actually a discrete time step that you're measuring it at. So each one of these time steps, you're going to take the vertical difference, and you're looking for the absolute value, because you don't care whether it's above or below the smooth line. You care about whether there's a difference. So you'd be looking at this one, 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 this one. And the idea here is that you sum up the amount of difference over a lap, and then the difference between those things, between the smooth and the non-smooth, is giving you a smoothness calculation on your brake pressure. And both of those techniques, both in terms of looking at derivatives and looking at smoothness, are applicable to lots of different parts of the data analysis, definitely not just braking. You're using those all over the place. So they're good questions. Did I find it useful? Yeah, definitely, absolutely. It's a way that you can basically put a metric on things without having to dig down to the nitty gritty of the data. If you just you can make a report really quickly, just looking at these what they're often termed KPIs, or key performance indicators. The idea, it's giving you some sort of zoomed out metric across the entire, whether it's at an entire race or a run or whatever it is. You can just look at these metrics and very quickly learn a lot about the way the car's being driven, the way it's behaving, just by looking at these metrics, rather than having to go through line by line of squiggly line and actually compare the way it's being driven. Typically what you're doing is using these metrics to point you into things in the data that are actually interesting, rather than going through the data line by line, which is really, really time intensive and not particularly good use of your time either. Okay, a question from Mike N. Mike asks, does a data analysis course go into some depth regarding math channels and creating math channels? Yeah, absolutely. So we got two courses, just to be clear. We've got our fundamentals course, our fundamental data analysis course. And the second course, the one we just released, is the professional motorsport data analysis course. So both of those courses, they're sort of designed to go together depending on your level, depending on how experienced you are with this. If you're already well versed, you're already making quite a lot of use of motorsport data analysis, it may well be that you don't need to take the fundamentals class. and you can go straight to the professional level course. Although I would say, if you're not sure, probably start with the fundamentals and then move on to the professional course. And saying all that, the professional course is the one that dives into a lot of detail about math channels, looking at why we use them, different methods, whether it's trig functions or calculus functions, or all sorts of different ways you can link things together and set them out. Yeah, it does go into quite a lot of detail on that. It's certainly, I think we actually do some, I'm sure we do some details exactly along the lines of the question Shane was asking around derivative and smoothness calculations as well. So yeah, happy to answer any more specific questions if there's something specific you're looking for in motorsport data analysis, but it is quite in depth. And if you actually head across to the website and have a look through the curriculum, you'll see a little bit more information about what exactly we cover as far as math channels. Okay, Max Kazabelski. Max asks, is there a good way to flag over travel in telemetry caused by leaks/brakes failure before they have the oh shit moment of realizing they have no brakes? Yeah, so unfortunately, yes, you can. It's the short answer. But the problem is at the same time that they're going to have that oh shit moment where they're going to press their brake pedal and it's going to be too long and they're not going to work, or the pedal's just going to be a lot longer than they expected, you're going to have no time to warn them over the radio anyway. So unfortunately for that particular situation, it's not going to be particularly useful. What I would say is what we looked at towards the end of the lesson I did, where I was talking about using brake travel versus brake pressure. If you're tracking that as a metric throughout the race, as I said, the slope of that line, if it's something that's slowly changing over the race, let's say you've slowly got brake fluid boiling and you're introducing more air into the system, you know that the brake stiffness is going to be getting lower and lower, so that slope of that line is going to be getting lower and lower. If that's something you're tracking, you can go ahead, either look at it manually or you can put some metrics on it and track it over time. But apart from that, if it's going to happen instantaneously, it's probably not going to be too useful for you. But yeah, that's all the questions we've got, guys. That was really great questions. Really, thanks very much for putting those through. I think they were really useful to have in there, and it's obviously you guys are really thinking about this stuff in depth already, which is fantastic. So guys, that's all we've got. I hope to see you guys around the forums. If there's anything more that comes up based on this, feel free to jump in the forums and ask your questions there. I'm sure we can dig into a lot more of this analysis chat. Thanks very much, guys. I'll see you next time.
That was just a taste of what we put on every week for our HPA Gold members. Our Gold members are able to watch these live and ask questions and get answers while we're presenting. After the webinars have been hosted live, they're added into our webinar archive where our Gold members can re-watch them at their leisure. We've currently got over 240 hours of existing webinar content covering topics on engine building, engine tuning and wiring. This is one of the fastest ways to expand your knowledge on a wide range of topics, as well as to stay up to date with the latest tools, trends and techniques in the performance industry. Our Gold members also get access to our private members-only forum, which is the best place to get fast answers to your specific questions. Gold membership can be purchased for just $19 per month. However, you'll also receive 3 months of free access with the purchase of any of our courses. Click the link in the description to learn more.